Notice, of course, this is going to be about sequences. We're in a sequence chapter. We're looking for patterns, obviously. I'll tell you this to kind of give you a preview of how writing these go. The math involved really isn't that bad. The worst thing you have to really do as far as the math is, I don't know, factor, distribute, combine some like terms. It's not too crazy. It's all the steps to write out a proper mathematical induction proof that is tedious and detailed. So we need to go through all of that good stuff. Okay, so first, a little bit of reading for us. There are two aspects to mathematics, discovery and proof. And they are of equal importance. We must discover something before we can attempt to prove it. We're looking for that pattern, obviously. We cannot be certain of its truth until it's been proved. That's where we come into play. So in this section, we're going to examine the relationship between these two key components of mathematics more closely. So let's try a simple experiment. We add more and more of the odd numbers as follows. So we start with 1, 1 and 3, 1 through 5, 1 through 5, 7, so on and so forth. You can see it. What do you notice about the numbers on the right-hand side of these equations? You should observe a pattern. They're all perfect squares. Okay. So far, so good. So it's important to realize that this is really still just a conjecture, though, because I've only tested 1, 2, 3, 4, 5 cases up there. So we cannot conclude by checking a finite amount of cases that it's going to work for all of them. We want to think about the infinitely many cases. So I'm on the blue here. To see this more clearly, suppose someone tells you that he's added up the first trillion odd numbers and found they do not add up to 1 trillion squared. What would you tell this person? Okay, who has time to add up 1 trillion squares?
Probably me.
Wouldn't that take forever? Nobody's going to do that. I would tell them you're crazy. You crazy.
You pray, girl. You pray, girl.
That's what I tell them. Okay, so it would be silly to say you're sure it's true because we've already checked the first 5 cases. However, we want to start checking it ourselves. This would take an incredible amount of time if we wanted to check that this pattern works for all the cases. Clearly, like I said, I only did the first 5. So what we're going to be working on, the power of a mathematical proof. We're going to use what's called mathematical induction today. Clear argument demonstrates the truth of a statement beyond doubt. That's what we're all about, beyond doubt. So, it looks like it's going to be easy. You think, oh, 2 steps. How hard are 2 steps? First step is easy, okay? So the first step, you just want to prove that they're going to give you a formula for a sequence. You want to prove that that formula does generate the first term of the sequence they give you. Super easy. You put the 1 in for n, bang, bang, boom, they match. Easy. Here, number 2 is where it gets dicey. The truth of pk implies the truth for p of k plus 1. Now we've talked about these subscripts when we did our recursively defined sequences. Remember, k plus 1 is the next term. So we are proving that the formula is going to work if I add a term to the sequence. That's what we're after today. That's where the algebra and math is going to come into play. So just to warm us up. Here. Okay. This isn't very hard, I promise. So we're just going to practice for right now before we get to the proofs, finding that next term. Okay, so simple math. I'm basically replacing all the k's everywhere, all the k's, with a k plus 1. Now, k squared, I'm going to put it in parentheses. I'm going to make that k plus 1 squared. Now, here's where you have to do a little bit of mental math. If I replace this k with a k plus 1, what is this expression combined to? K plus 2, the next term. So this is going to be some of the first steps, again, warming you up, baby steps. Some of the first steps you're going to do. You're going to replace k with a k plus 1 because we're proving the formula works if I add a term. Moving on, same thing. I'm going to replace all the k's with a k plus 1. Same deal. So 1. So much writing, so much writing. I feel like I'm going to run out of room. I'm definitely running out of room. I'm just going to put it underneath. Okay, so and I'm going to, what we're doing here around here. So again, So this one's a little different than the last one. Again, warming you up baby steps here. We are adding, notice I switched to red here. We are adding in the sequence the next term. We're gonna go back. I'm gonna replace both of the k's with k plus 1. Now notice the k is in two expressions, so we're gonna have two expressions here. So I just copied down what we started with. Now a little mental math, if you put k plus 1 in here, you've got the 4, you're going to have the 1's canceling. So I'm going to have 4k minus 3 for that. Right, that's supposed to be a k, a sloppy k. So that would give you the next term. I've got a second one. So if I put k plus 1 in here, so I'm going to have 4 times k. Now, what's 4 times 1? Minus 3. Okay, so hold on. So a little different than the last one. Last one we just had the equation, the formula, you just had to do it, which is going to be part of our skills today. Some of the skills today, they're going to give you the sequence. They want you to add the next term. Now, for our terms, the k's are in two expressions. That's why I added 2 blanks. That's why I just swap out both k's with k plus 1. Most of the time, you just have one expression for k. You just have to add 1 blank. But we have 2 this time, so 2. C is easy. Another easy one. Little everything for today.
I would not say B is.
B is not easy. C is easy.
So,
So this just k plus 1. Now, if I put k plus 1 in here, 2 times k, easy. 2 times 1, 2 plus 1. So make sure also you're distributing that 2 to both the k and the 1. So an easy one. So we have to kind of be good at both skills, meaning just a straight replacement of k plus 1. We didn't have the full-on sequence. We're going to do this today. That's easy. And if I give you a sequence of terms, adding blanks for the next term or terms, depending on how many expressions. Not even to the proofs yet. Are you excited? Okay. I'm excited. I love this stuff. Here we go. So there's your expression. Here's our sequence. Here's our sequence. So here's what we're going to be working on. Easy question. What is the sum of the first term?
3.
3. Sum of the first term is 3.
Oh, you're so smart.
Gold star on.
Easy. Easy enough. Gold star on. Do you get the same value when you replace n with 1 on the right side?
Maybe.
Let's test it. If I do 1, 2 times 1 plus 1, does that give you 3?
What? Yes, it does.
3? Agree?
Yes, it's 3.
Okay. So this is basically, we're working our way to it, the first step in your mathematical induction. You want to show me that when you put 1 in for n on the right side, you get the first term. Easy. Okay. What is the sum of the first 2 terms? 10. Do you get the same value if you put 2 on the right side? So if I do 2 times 2 times 2 plus 1, does that give me 10? Okay. What's the sum of the first 3 terms? Probably can make a guess here. Do you get the same thing if you put a 3 in on the right side?
Yeah.
Yeah. Okay. Now, you know I love to review. I can't help myself here, kids. So think about your quizzes Friday. There is a problem on there that asked to find the first 4 partial sums. First 4 partial sums. Some of you just straight added the first 4 numbers and gave me that answer. There should be 4 answers. Some of the first, some of the first 2, some of the first 3, some of the first 4. Some of us didn't read that closely. Read plus. Okay. All right. Moving on. I got off track. Question for you. And I'm not writing out 28 terms. You're out of your mind if you think I'm going to. Do you think that this hypothesis would hold true for, say, the first 28 terms? I think so. I'm with you, Kale. I'm thinking yes.
Yeah, Cal.
But clearly, I don't want to write out 28 terms and show that it works if you put 28 in paren. That's obnoxious. So here's where we're going to use our mathematical induction. Our proofs by mathematical induction. Okay, so step one. Prove that it works for the first term. So let me click it back. I'm going to be back and forth. Basically, we're working on this sequence. We already did that in this first step. I want to prove that it works for the first term. So I want to show that 3 is 1 times 2 times 1 plus 1. What we have in red, that's what I'm writing. So I'm going to show that 3 equals our 1 times 2 times 1 plus 1. So that's the very first step. You are showing that the formula on the right side works and gives you that first term. Of course, that's 3. I should have wrote a little smaller. I'm just going to put an accent point. Sorry. Okay, next step. Here's the fun step. Are you ready? You want to prove that it works for the next term. So this is our first official mathematical induction proof we're going to write for that sequence. So there are some, I know, I feel excitement. There are some little details that we have to put into this proof. So get ready. First up, write small. We're going to say assume, which always bothers me to write assume, because we're showing for the next term. Notice they switched the variable from n to k. Here's why. Because again, I'm trying to prove that the formula works. So for right now, while I'm working on that, we're going to use a different variable. Does it have to be k? I mean, not necessarily, but we're always going to use k just to keep it consistent and we're all in the same place. So I'm going to assume p of k is true. So that is one of the things you need to have written in your proof. So, and again, yours right above you. So I'm basically rewriting this equation, but with a k. That's my next mission here. So I'm just rewriting that 3 plus 7 plus 11 plus dot 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 for k minus 1 equals everything with a k now. Okay, so we got it in front of us. Ready for the next step?
No.
I'm ready.
Okay, now goal is, so here's my original sequence. We want to show it works for the next term. So I want to add a term into this sequence. So I'm going to, let's keep the green here. I'm going to keep my 3, my 7, my 11. Lot to write out. And I'm going to add a term. I'm going to worry about the right side in a second. Now, to add your term, just like that first example, I'm going to go back to my previous term. Some of you can mental math it. I'm going to write it above it, and I'm going to replace that with a k plus 1. So I'm going to have 4 times k. 4 times 1. What's 4 times 1? And then combine it with your minus 1. 3. So that would be your expression for your next term. So first, I'm going to stop for a minute. Any questions on the 4k plus 3, because that's critical. That's not what I asked, but I love it. Okay, now, right side, same thing. We want to show it works for the next term, so I'm going to replace this with a k plus 1. Now, do I expect you to write this above these like I am? No, but I'm going to do it, of course, for your notes so you know how I'm getting this. And I'm going to replace this guy also with the k plus 1. So again, I'm going to wash my algebra here. 2 times k, 2 times 1, 2, 2 plus 1, 3. All right, so let's hold up the truck. Any questions right now on how I get anything in the blue? Okay, our goal is to show the left side equals the right side. So now I'm doing the algebra and the math to make it happen. I'm going to use some old school substitution. Okay? Because we know from 3 up to 4k minus 1, I know that that equals this. Because I don't want to keep writing this. I don't have all of this craziness over on the right-hand side. So I'm going to use some substitution. I'm going to replace the 3, the 7, the 11 with k, 2k plus 1. So I'm using substitution. So that's the first big important step. Now I'm just writing all the other stuff I still have here, all the stuff in blue. And I'm just going to scroll it up a little bit so I'm not so far at the bottom here. Now I think I can, with just a little algebra, show these sides are going to be the same. What's your gut instinct? What would you do next? Yeah, let's distribute. 2k squared, k. Yeah, I know there's some like terms. I'll put them together here in a minute. I'm going to distribute the right side. 2k and k. I know some of you can probably do these middle terms together fine. Do the sides equal? If I clean them up?
I hope so.
They do. I hope so too. You have an error somewhere. You got it wrong. Still not done. We're still not done. We're still not done. So hold on.
What else?
So first off, let's just recap quickly. Because nitpicky steps, but these are all things you have to put in your mathematical induction proof. I need the assume pk is true. You're going to rewrite it with k's just to get it out of n while we work on it. Here's the big step. You're going to add the term, that's the blue, putting in the k plus 1 in the previous. And then the substitution is your other next big step. From there, it's usually just distributing, FOILing, combining terms, whatever, to show the two sides equal. Last step. Ready? Have you seen this symbol?
I've never seen it.
That means therefore.
I think that's me when I just like
Therefore, by mathematical induction, yes, you have to write that out.
By mathematical.
I'm
You
going
can
to
spell it.
that was my thing, just gonna be like hitting my pencil onto the test.
By mathematical induction, you gotta love it.
Do you have to spell it right?
That would be nice. PN is true. Or sometimes I'll have kids that say valid. I don't care.
Valid or bugging?
That is what you're doing today. Now, is it time consuming and tedious? Yes. How many are on your test Friday?
One.
It's time consuming. We can't do 20 of them. No. Ellie, were you going to ask me something?
I was gonna ask how you how you index the left side of k's times quantity 2k plus 1, but I see now that it's because
Okay.
initially it's equal to that.
Yep. I substituted. All right, let's do some more. 2 to go. Okay. Notice, I didn't really set it up for you. We're going from scratch, my friends. Okay, step 1. Now, do I care, like I'm actually going to write out step 1. I have sometimes you just put a 1 and number it. I'm going to, get fancy here. Step 1. So first mission, easy mission. We just want to show that the formula works, the right-hand side works to generate the first term. Well, my first term is 1. Does that work when you put a 1 in on the right side? Last time I checked, 1 equals 1 squared, yes?
Yep.
Yes. So, oh boy, that scares me. So you're just showing that it works when you put a 1 in. So I'm just going to say 1 equals 1 squared is true. Okay.
Next step I assume is
Now, next step is where we have to assume, step 2, assume, and again, notice they're using n in the formula. We're just going to use a different variable while we work on it. Always use k just to keep it consistent. So I'm going to put assume, instead of s at n, I'm going to put p of k is true. So I'm going to write out that equation. I'm just going to swap out all the n's with a k right now. So, okay. Let me give you a minute to write.
we have John.
So our goal is we want to show that this formula works if I add a term to both sides. So I'm going to keep the left. I'm going to keep it in green here. See, this is the irritating part. You have to write this out so many times. And we are going to add a term. So that means, just like that recursively defined, that's why I harped about that so much at the beginning, I'm going to go back to the previous term, and we're going to replace the k with a k plus 1. Now again, you don't have to actually write that. I know some of you can just mentally do it. Fine. 2 times k. 2 times 1 would be 2. I'm going to combine it with the minus 1, so I'm at plus 1. Does it matter if you put it in parentheses? No, I'm going to just for consistency's sake, because the last term's in parentheses too. Now, I'm changing the right-hand side because we're adding a term. So instead of k, what's your right-hand side? K plus 1. So now our goal is to prove that that equation, the left side, really does total you up to the right. And we're going to do that with substitution. Because notice, okay, we don't want to have all this 1, 3, da, 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 da. I know, I'm going to substitute it, 1, 3, 5, 7. I know that equals k squared from the previous line. I'm just going to substitute those in. So instead of me writing 1 plus 3 plus 5 plus 7, I'm going to put k squared. And then I have all the blue stuff still, plus the 2k plus 1 and my k plus 1 squared. Your job is to algebraically show me those two sides are the exact same. And you have choices on this. How are you going to do it? I could FOIL the right side. I could factor the left side. Multiply to 1, add to 2, I could factor that also. Do I care which way you roll on it? No, I just need to see the two sides are the same. I heard FOIL first, so I'm going to FOIL that side. So if I FOIL this out, I'm going to have k squared, I'm going to have 2k and a 1. Sides match, we crushed it. Now we have our final statement by the principle of mathematical induction.
We have to put the principle.
It's literally like 2 minutes away. I'm just saying by mathematical induction.
You can say by mathematical induction.
P of k.
We should get extra credit for today the principle.
Oh my goodness.
Instead of just
All right, what's the last of it? Let's make it easy. The formula is
True.
true. Formula is valid. Whatever.
Valid or boogie. Will it ever not be true?
Only if you mess up.
Fair
It's
point.
always true.
Everyone I've given you works out.
Okay.
Yeah.
Like
In
ever.
theory, you could have it where that formula does not work, but clearly with our first time, everything I'm going to give you works out. I'm not that mean. All right, ready for last one here? Last one stretch here? Get in there. Whew. Ha. All right, step 1. So first step, we just have to show that it does work for the first term, so which is clearly a 5. So if I put a 1 in on the right-hand side, real shocker there, we do have 5 equals 5. Second step is the pain one. So assume, I gotta write the word assume, P of k is true. So I'm going to rewrite out that formula. I'm just going to swap all the ends out with k's while we work on it. So 5. Okay, I'm going to scroll it up just a smidge here. So next up, we want to show that this formula is valid and it's true if I add a term. So again, I'm writing out all this 5, 7, 9, my favorite also here. Okay, and we are going to add a term. I'm going to give you a second to see if you can figure out what the term is. What's the expression for your next term?
5 plus 2k.
5 plus 2k for the
Good
win. Or
job.
2k plus 5, however you want to do it. Air high 5, Alex.
Thank you, Mrs. Byer.
You're welcome.
Never even look again, are we like?
Any questions on how to get the 2k plus 5? All we did is put a k plus 1 in this guy. Okay, I'm going to replace all this with k plus 1. So I'm going to have k plus 1 and then k plus 5. Now, we want to, of course, this is getting obnoxious, all of this stuff. We want to use some substitution. I know through 3 plus 2k it equals k plus 4. So I'm just going to swap those out. And then I have still all of the green in here, still all of the green involved. I got the 2K plus 5, and I have this right side. So your job is to somehow now show me algebraically that these two sides perfectly match, which I have a feeling some of you have already done. Do they match?
Yeah, probably.
Distribute.
Yeah.
K squared, 4K. So since I've got all these terms here, I'm going to FOIL this one out. K squared. Now, personally, I just do the middle terms in my head. You can too. 5K, 1K, 6K.
That's actually not that bad. This is not that bad.
And we do have the same thing over here. Would you rather do this or a geometry proof?
This.
Ooh, interesting. Okay.
Really? I can't remember all those terms.
Oh, all the vocab, all the theorems. Linear pair postulate, that sort of good stuff. The looks on your face is priceless. I love. Okay, final step. Therefore, by mathematical induction, what's the rest of it? The formula is valid. Fancy. Is it as bad as you thought or worse?
Over like Andy's shoe.
I like that attitude. Okay, so.